So next topic is finite difference methods. So in finite difference methods, we first introduced the concept of different types of PDEs. And this is one of the things that might appear in the exam. That is, what's the practical consequences of elliptic versus parabolic versus hyperbolic PDEs? You don't need to understand the exact mathematical definition, but like the practical difference is that an elliptic partial differential equation has a domain of dependence of everywhere. That means if you change the coefficient, change the right-hand side, change the differential operator of the PDE anywhere in the space domain. Usually elliptic PDE doesn't have time, right? So if you change the differential equation anywhere, it will have an impact at everywhere else in the domain, right? It's kind of a it's some kind of an instantaneous effect, okay? And an example is a structural system. So if you have a structural system, you put a force anywhere, you have deformation in the entire structure. Okay, at some points the deformation may be small, but it's going to be finite. So this is elliptic. Parabolic, first to say hyperbolic. Hyperbolic is the other extreme. If you put any perturbation in the system, the effect of the perturbation propagates in the time domain and at a finite speed. Okay, wave equations are the primary examples of hyperbolic PDEs. And in fact, many PDEs has wave-like behavior, like fluid flow problems. So these are typically hyperbolic PDEs. So parabolic PDEs are somewhere in the middle. It has a time, but if you make any perturbation, the perturbation is going to have an instantaneous effect over the entire domain. But because it has time, the perturbation is not going to propagate backwards in time, right? So it's like any perturbation is going to have effect on the entire domain, but only after the time of the perturbation. So that's really the difference between elliptic, parabolic, and hyperbolic. So elliptic means if you perturb a system here, the information propagates like in all directions. So elliptic.
Can it be instantaneous because there's no time?
Instantaneous, right? There is no time. And hyperbolic. So now we have time and space. If you make a perturbation here, the information is going to propagate only at, use red, the information propagates at finite speed. So only this domain is changed. The effect here is exactly 0, okay? And for a parabolic, we also have time. And here, if you make a perturbation denoted using blue, the information is propagating at infinite speed. Actually, it's going to affect everywhere else, but only after the perturbation. There is a causal effect in parabolic equations, but not in elliptic equations. So that's why elliptic equations usually don't have time. Okay, so what type of equations can finite difference solve? All types, right? As long as the derivatives in the finite difference, in the differential equation make sense, which means there is no discontinuities, okay? And it can actually solve equations in any kind of complex domains, but it becomes very difficult and often not so accurate if you have complex domains. So it's the best for differential equations that have smooth solutions and the domain is regular. Okay, so that's the strength of finite difference. And it's very easy to get a high order scheme in finite difference. So some basic finite difference approximations, partial u, partial x equal to something, right? You should be able to kind of know or familiar. Second order derivative. So these are the kind of the two types of derivatives that you should now be familiar with using finite difference method. And also how to analyze the accuracy of finite difference approximations. Okay, so these are also using Taylor series analysis. The tool you use is exactly the same as the one you use in analyzing local accuracy in ODEs. So stability is a topic that we went in a little bit, but not too much, right? So the first thing you have to know is the stability, just like in ODEs, is the crucial link between the accuracy of the derivative approximations and the accuracy of the final solution. If you don't have stability, then even if all the derivative approximations are super accurate, your final solution may be garbage. If you have stability, then the order of accuracy of the approximation and the order of accuracy of the final solution is going to be the same. All right, so this is the consequence of stability. Now, how to analyze stability? The thing we talked so far is we discretize the partial differential equation into a system of ordinary differential equation, right? And if the differential equation is linear, the discretization is going to get us a system of linear ordinary differential equations. And after that, how do we analyze stability? Matrix, right? Eigenvalues. I mean, if you have a system of linear ODEs, you can write ODE into a matrix form. du dt equal to a times u, potentially plus a constant b. And the eigenvalues of a is going to go into the stability region of whatever ODE time integrator you are using. Right, so basically the stability of a finite difference PDE discretization scheme can be analyzed by converting the PDE into ODE and perform eigenvalue stability analysis on the ODE. Right, so we performed that type of analysis for a particular type of differential equations, du dt plus a big U times du dx equal to 0. And we found that in order for the system to be stable, we have to have in order for the system to be stable, we can use a central difference, or did we study upwinding in this context? I think we studied upwinding, right? So the scheme would be more stable if we do upwinding. If we do central difference, the eigenvalues lies exactly on the vertical axis, on the imaginary axis. So it's neither stable nor unstable. If we do upwinding, the eigenvalues are shifting towards the negative part of the real axis. So the scheme is more stable and you can use forward Euler to solve it. If you do downwinding, which doesn't really make any sense physically because the propagation of information is from the wrong direction, then the numerical manifestation of that is the eigenvalues are shifting towards the positive side, and you are not going to be getting a stable solution even if you can solve the resulting ODE analytically. So this is about stability and how the consequence and how to analyze it. Okay, if you kind of go into the more advanced graduate version of how to solve PDEs, you're going to learn all kinds of more type of methods to analyze PDEs and its stabilities. Okay, so that's basically finite difference, what you need to know about finite difference.